Very well. We will continue with the Laplace transform properties. We have seen some properties of Laplace transform already. I think it was the third property, which was corresponding to time scale versus scale in the Laplace domain. And since we are scaling the Laplace parameter of S, the region of convergence is also changing, and it needs to be reformulated. Let's continue. The fourth one then, the fourth property could be the conjugation. So what is the Laplace transform of x conjugate of t? If x of t has a Laplace transform of capital X of S, then what's the conjugate of this one? The conjugate of this one is capital X conjugate of S conjugate. And you may remember this or memorize it if you wish by seeing that x conjugate of t in the Fourier domain had a Fourier transform of x conjugate of minus j omega. That was the property in the Fourier domain. Now, minus j omega means we are negating the imaginary part of S, the j omega part, but the sigma part does not change. So we notate it as S conjugate. And the region of convergence does not change. It was the same as the previous non-conjugated thing, because as we see, the real part is the important limiting position for the region of convergence, starting point or ending point or whatever. So since none of the real parts of the poles may change, that doesn't change anything in the Laplace transform region of convergence. As simple as that. The next one is the convolution property, which we have been using implicitly, but now we can write it. If x1 of t is convolved with x2 of t, then in the Laplace domain, of course, their Laplace transforms are just multiplied. And that is the system response behavior. For instance, if x1 of t is the input signal, and let's say that x2 of t is the impulse response, which could be h of t, then in Laplace domain, we are just multiplying, just like what we are doing in the Fourier transform. So the system response is generated in the Laplace or Fourier domain. And what's happening in the region of convergence is the next issue that we have to resolve. The region of convergence includes the intersection of R1 and R2 as usual, which means pretty much nothing, because during the multiplication of x1 of S and x2 of S, poles and zeros may be cancelled. For instance, if you have, for example, S plus 2 over S plus 1 as the Laplace transform of x1 of t, which is x1 of S, and x2 of S could be S plus 1 over S plus 2, and they just cancel one another, and you have 1, and the region of convergence is the, it becomes the entire S-plane with no bounds or anything, just everything is canceled. So in general, you have to be very careful about pole zero cancellations after the operation that you are doing. If you're multiplying with, if you're multiplying or adding two terms in the Laplace domain, some pole zero cancellations may perfectly appear. The next property is differentiation in time. And I will also show you the differentiation in the Laplace domain too. So let's call the property to be differentiation only. If you take the time derivative of the time signal x of t, then its Laplace transform will be simply multiplied by s. So at long last, we have seen this proper notation of the derivative in the Laplace domain. In the Fourier transform, we were using j omega because it's essentially s with sigma is equal to 0. So this is a very convenient way of putting the differentiation operator in the Laplace domain or in the system domain. However, again, the region of convergence is an issue, and the region of convergence here just includes R, I will have to say, which was the region of convergence of x of s. Why do I say it includes? Because it may be larger. Under which circumstances can it be larger? For example, x of s may have in the denominator a term like s. And then, so we have numerator of s over s times denominator prime of s. And then we suddenly multiply it with s, and these two s's will cancel one another. And the denominator's s multiplication, if it is the decisive boundary for the region of convergence, then it is now gone, and the region of convergence probably became something else. So you have to be careful about cancellation of a pole at s is equal to 0. A pole could be cancelled at s is equal to 0. Okay. That is the only thing that you have to be careful about. And this d by dt operation making s times x of s in the Laplace transform also iteratively continues with further derivatives. If you take the second derivative, d squared by dt squared of x of t, clearly it would correspond to an extra multiplication with another s in the Laplace transform. Therefore, the Laplace transform would be s squared times x of s. All right, it goes on like that. And it is a very convenient tool to use, especially in converting the differential equations. Previously, we were converting differential equations into j omega polynomials, but now we are converting them into s polynomials, s to the power n times something plus s to the power n minus 1 plus times something, etc. They would correspond to the differential equations. That's a very convenient way of attacking those problems. Just convert the differential equation into the Laplace transform. In fact, that's what we have been doing in the differential equations courses. In some cases, we were using this S parameter. But that differential equation versus Laplace transform is a little bit different. I will come back to that. It's a Laplace transform which has an integration starting from 0 and going to infinity. And since it's not extending to minus infinity, the whole history of the signal is not depicted, and therefore we need, for instance, initial conditions. Initial condition of x of t at t is equal to 0, or initial condition of its derivative, etc. They will be needed. We will come to that. Now, there is some sort of a duality in the Laplace transform too, but I'm not going to list that out. You can always find the list of properties of the Laplace transform in the book. I will indicate which page you can find them. I'm just indicating some of them. And if you use that duality property, from the duality, something like this also happens. If you take the derivative of x of s expression, it's an expression of s, and if you take the derivative with respect to s, then that would also correspond to a time domain signal, this time on the time axis in the form of minus t times x of t. Okay, it's like you take the time derivative and you multiply by s in the other domain. You take the s derivative and you multiply by t in the time domain, only with a sign change. And the region of convergence for this one, by the way, is exactly equal to R. I don't say it includes or anything. That's an interesting observation, because you can say that if you take the time derivative of a numerator over a denominator, things may change, and you're right about that. Things essentially change. For instance, if you have n of s over d of s, and if you take the time derivative of, of this thing, now this thing from the definition of the derivative, remember from calculus, n prime of s ds minus d prime s and s over ds, excuse me, ds square, right? It was happening like this. Now, the denominator is therefore becoming the square of the previous d of s when you take the derivative. So, for instance, if you say that d of s is equal to, let's say, s minus 2, this is an example. If ds is s minus 2 in the denominator, that means there is a pole at s is equal to 2. And depending on whether it's right-hand sided or left-hand sided, let's say it's right-hand sided, it's to the right of 2, which is not convergent, by the way. It's an unstable system, if it's a system response we're talking about. But when you take the derivative, ds square will become s minus 2 square. So now where is the pole? The poles will still be at s is equal to 2, but now we will have 2 poles. We may have 3 poles, 4 poles, whatever, but the poles will still be at the same point, s is equal to 2. And since they don't change their locations, the region of convergence does not change. We're just incorporating some extra poles to the system, but at the positions of wherever they are before. Previously, they were at s is equal to 2. Now they are again at s is equal to 2. So their places do not change. They just multiply in number. And therefore, the region of convergence does not change when you take this s derivative of n of x of s. So that is a property that we have to understand. And we can now see one example of application of this property, which is this. What is the Laplace transform of t times e to the minus at u of t? Okay, that is the question. Now, if you encounter such a question, you must immediately recognize that it is related with this property that we have seen, because we are multiplying a known signal, which is e to the minus at u of t, that's something that we already know, with t. So since we are multiplying with t, it must correspond to something in the Laplace domain by taking the s derivative of that Laplace transform expression. We know that, in other words, e to the minus at u of t will have a Laplace transform of 1 over s plus a, right? So when I take the derivative of the right-hand side of this transform arrow, that would correspond to a time domain signal, which is minus t times e to the minus at u of t, right? So let us see what is d by ds of 1 over s plus a, and or we could also write it like then t times e to the minus at u of t, a Laplace transform which is equal to negative of d by ds 1 over s plus a, and that is the negative of the time derivative would be minus of minus 1 over s plus a square, which is 1 over s plus a square. So this is it. This is the Laplace transform of x of t that we have in the question. Now this also shows you a nice way of how the terms are changing. At the right-hand side, we used to have 1 over s plus a. Now we have 1 over s plus a square. What would happen if it is 1 over s plus a cube, or to the power 4, to the power 5? In general, to the power n, in other words. If you go on like this, then if you say that the right-hand side is 1 over s plus a to the power n, what kind of a time signal would it correspond to? It actually corresponds to iteratively multiplying with t n minus 1 times. And by the way, it also, of course, now starts generating some coefficient, because 1 over s plus a's derivative is 1 over s plus a squared, but the derivative of 1 over s plus a squared now has a factor of 2. Therefore, we have to incorporate that power term. So it essentially becomes like this: t to the n minus 1. This is where everything comes from. And there's e to the minus at u of t. But there is a denominator of n minus 1 factorial, because we multiply by 2, and then we multiply by 3, then 4, etc. So it grows, that multiplication, which must be compensated at the left-hand side of the transform equation. So this is also something that usually exists in typical transform pair tables. So in the table that will be provided to you in the final, you will most probably have this one too, okay? It's a very typical thing. If n is equal to 1, then the left-hand side of this transform equation automatically becomes e to the minus at u of t only. Okay, so it's just a special case. Integration is the opposite of it. Which number was this? It was 6. So now 7 is integration. And it's also quite trivial in a sense. If you integrate from minus infinity to t, the signal, the time signal, so it's from minus infinity to t x of tau d tau, that is the integral of x of t. Then the Laplace transform is very simply 1 over s x of s and nothing else. We don't have any other coefficient. Now the region of convergence, I don't know if I really need to write this, because you have to evaluate, because there is a 1 over s over there, right? So that 1 over s just puts a pole at s is equal to 0. If you didn't have it before, now you have it. Therefore, you now have a pole at s is equal to 0. If all the other poles are, let's say, to the left of 0, j omega axis, then now you have another pole at s is equal to 0, and if it's right-hand sided, then it means that your new region of convergence is to the right of 0. But if you have other poles that are already at the right of 0, then it means the region of convergence did not change. You just incorporated a pole which is already out of the region of convergence. So I could write it like the region of convergence includes the previous region of convergence of x of s, which we denote as R, intersection with a new region of convergence as real part of s is greater than 0, because that 0 point may indicate that region of convergence. So that's the intersection. But again, some pole zero cancellations may occur. Therefore, I'm just saying that it includes, to be on the safe side. Just evaluate that. By the way, there's another way of interpreting this result. This is the Laplace transform. 1 over s is the Laplace transform of u of t, and x of s is the Laplace transform of x of t. So I'm convolving them in time domain and taking the Laplace transform of the expression, and I get a 1 over s x of s. That's why we can say that integration of x of t, integral of x of t, is essentially x of t convolution with u of t in the time domain, okay? Please also remember this. It helps understanding. And the last properties that I want to talk about is not the these are not the last properties. Of course, we have several other properties, but these are the ones that I want to just talk about during the lecture. You have to check the other properties. You have to solve questions regarding those things, etc., all from the book and from any other resource that you may find. the limit and initial values of the time domain signal x of t. X of sorry, my throat. X of 0 plus, which is x of t at t is equal to 0 plus, or as t goes to 0 plus. That's the initial value at the positive side. In case there's a discontinuity, this is 0 plus, okay? The right-hand side of the discontinuity we're talking about at x of 0 is equal to s times x of s as limit s goes to infinity. The proofs of these are not very difficult if you consider the Laplace transform formula and see what is happening as s goes to infinity. And you will be able to find the proofs of these, but they are beneficial if this question is particularly asked. For example, you need to know the initial value of a signal, which you don't know, and you are given a very complicated zero. There are two things that you can do. One of them is the hard way, the difficult way. You can just try to take the inverse Laplace transform. Terrible idea, a very bad way of solving this question, but it's possible. So you try and try and try, and you come up with an x of t expression in terms of t, and put t is equal to 0 and see what x of 0 is. You can do that, but I wouldn't recommend it. If you're only looking for x of 0, then please just apply this. Multiply the x of s, it may be a complicated expression of x of s, multiply it with s, and see the limiting value as s goes to infinity. It may go to a finite value, it may go to a 0, or it may go to infinity, and then you say that x of 0 is that, okay? As simple as that. For example, for u of t, let's apply it immediately and see it as an example. U of t at t is equal to 0 plus. What is this thing? It's equal to limit as s goes to infinity, s times, what was the Laplace transform of u of t? It was 1 over s, which is 1. And we see that u of t at t is equal to 0 plus is equal to 1, because it rises to 1. U of t rises to 1 and stays that way, okay? So this is an application of the initial value. The limit is the opposite. What is happening as t goes to infinity to the time signal? Where does it go to? Where does it end at? And again, this is as s goes to 0, s times x of s. Okay, so it's just the opposite. We don't push s to all the way up to plus infinity, but we say that s is now 0. And as at s is equal to 0, what is the limit? Again, if you consider the same example as this one, u of t, which is 1 over s, s times 1 over s is equal to 1. As s goes to 0, it is still equal to 1. And therefore, as t goes to infinity, x of t, or u of t at t is equal to infinity, will be equal to 1. It will stay as 1. Okay? You don't have to invert the Laplace transform if you're only looking for these limits as t is equal to 0 and t is equal to infinity. What's happening on the boundary conditions? So this property will help you to solve these things. Now, I will put an end to this, and I will elaborate a little bit more regarding the derivative theorem. When you take the time derivative of x of t, it corresponds to s times x of s. It will help us to solve questions easier than the Fourier transform technique, which is still available to us. The Fourier transform technique requires s is equal to j omega, and the Laplace transform technique requires just the utilization of s, as we know. So let's do it. Let's see some examples of these. For example, we make an experiment. X of t goes into a linear and time invariant system with an impulse response of h of t, which we want to determine. We don't know. And y of t is being observed. Now, before the knowledge of the Fourier transform or the Laplace transform, the only way to determine h of t is to literally apply delta of t, which is an impulse, as the input, and the output will therefore be the impulse response. Impulse and its response. Of course, application of an impulse is not possible. So instead of that, you could also, if you're smart enough, you could also apply a u of t, a unit step, which is a manageable, much more manageable signal. You apply a unit step and measure the output. You draw it, and then say that that output is actually not the impulse response, but the integral of the impulse response. Therefore, I need to take the time derivative of the that output. Let me take the derivative of it. Now that will be the impulse response. One of them will be the step response. So the derivative of the step response will be equal to the impulse response. But now we have more than that. By knowing the Fourier transform or the Laplace transform, we can just apply any kind of an experiment. We could, for instance, apply this input, x of t is equal to e to the minus 3t u of t. Okay, we just feed this input, and we make an observation of the output, and we observe that the output is equal to e to the minus t minus e to the minus 2t u of t. This is the output, and it looks perfectly fine. Clearly, in doing experiments, you don't really come up with such analytical formulas, but you come up with data. From that data, you have to extrapolate what is the analytical meaning of that. But nevertheless, let's assume that we made the experiment, and this is the input, and this is the output. Now, how can we find, for example, the impulse response, differential equation relating this input to this output? Okay. And the way to approach this problem is through the Fourier or the Laplace transform. By the way, the Fourier transform is very much available for this input-output because both the input and the output are convergent. They are decaying exponentials. But let's use the Laplace transform because it's easier. The Laplace transform of the input is S1 over S plus 3. And the Laplace transform, let me also write the region of convergence without forgetting this. It's to the right of minus 3 because the input is right-hand sided. Therefore, the region of convergence is to the right of the pole, which is at minus 3. Here, y of s is equal to actually two things. It's 1 over s plus 1 minus 1 over s plus 2. And when you combine this simplified form, which is nice, this, and the region of convergence is real part of S is greater than minus 1. This is also right-hand sided. There are two poles. One of them is at S is equal to minus 1. The other one is at S is equal to minus 2. And the region of convergence is to the right of the rightmost pole, which is minus 1. It can't be to the right of minus 2 because then minus 1 will be inside the region of convergence, which is a pole. And we don't have any poles inside regions of convergences. Okay, so this is the region of convergence. So what is h of s? H of s is y of s divided by x of s. Why is this formula correct? Because y of s is equal to h of s times x of s. Convolution will reflect as multiplication in the Laplace domain, which will help us to discover h of s as if in the form of a division of y of s to x of s. You can also write y of j omega divided by x of j omega, which is also true, but you cannot do this in time domain. You cannot just divide. it's impossible because their relation, the relation of x and h is in the form of convolution. X convolution h is equal to y. So x is what? You cannot resolve it in time domain. You cannot deconvolve in time domain, in other words, easily. But in Laplace or frequency domain, you just divide y of s by x of s, as simple as that. S plus 1, S plus 2. So this is the system response. The system response. It is called the system response. If you put S is equal to j omega, it will convert into frequency response, which is also a kind of system response. Bayezid asks something in the chat. Let me, xs times hs is equal to y of s, but in time domain, it is convolution, right? Yeah, that's exactly what I'm talking about. X of t convolution h of t is y of t. Therefore, you cannot say h of t is x of t, sorry, y of t divided by x of t. Many students tend to do that. It's not correct. You cannot divide in time domain. You have to divide in the Laplace domain or in Fourier domain. So this is known as the system response. And if S is equal to j omega, it's the frequency response. If you take the inverse Laplace transform of this, which you can do that, okay, then that would mean you found the inverse Laplace transform of capital H of S is H of T, the impulse response. That's how we do it. But now I'm not going to do it for this example, and I'm leaving it for an exercise. Please, as an exercise, find the inverse Laplace transform of this expression, which is H of T. And how are you going to do that? You have to split this term into summations. A over S plus 1 plus B over S plus 2 will be your answer, or A will be your new H of S, where you have to find A and B, of course. When you combine it, it's going to give you this. And from that, A and B, A over S plus 1 and A over S plus 2, B over S plus 2, you will easily find the inverse Laplace transforms. They will be e to the something times e to the minus t u of t plus some other thing times e to the minus 2t will be your impulse response. But what is that? Please do it. But now I will do something else. I will find the differential equation of which describes the input-output relation of this system by just making cross multiplications of y of s with the denominator and x of s with the numerator. Let me multiply them. And it's going to give me, but of course, for this, I have to find this in a polynomial, regular polynomial form, and that is s squared plus 3s plus 2. I can also write it like this, right? So now I'm going to do the multiplications, and it's going to be s squared y of s plus 3s y of s plus 2y of s will be equal to s times x of s plus 3x of s. This equation is in the form of s polynomial coefficients. Therefore, when I take the inverse Laplace transform of both sides of the equation and convert them to time domain, they will give me, it will give me the differential equation. S squares inverse Laplace transform is a double derivative, d squared by dt squared of y of t plus 3s, 3 times d by dt, that is, of y of t, plus 2 times y of t, okay, because y of s inverse Laplace transform is y of t, and side, S times x of s inverse Laplace transform is d by dt x of t plus 3 times x of t. So this may be the thing that we are asking for. But how many variants did we have? We have this differential equation. It's one form. We have h of s is equal to this, which is the system response, another form. Or we can have h of t, which is the inverse Laplace transform of h of s, that could be asked. And finally, we could give an experimental input and output result in this form. X of t is something, y of t is something. And as long as it's linear and time invariant system, it can only correspond to one distinct and unique system. So these four things, four green boxed things, they all describe the system. And one of them could be given to you, okay? And the other one can be asked. I can give you, for example, h of t, and I can ask you what is the differential equation. What's the thing that you're going to do? From h of t, you take the Laplace transform and get h of s, and say that h of s, so from h of t, you get h of s by the Laplace transform, and say that h of s is equal to y of s divided by x of s, and you write the Laplace transform here, and then make the cross multiplications, and you come up with this expression, and then finally you take the inverse Laplace transform of that to come up with the differential equation. Or I can give you the differential equation and ask you what is h of t. Then you have to take the Laplace transform of this, obtain this. From here, isolate y of s and x of s at two parts and write y of s divided by x of s like this, and you say that that's equal to h of s. You may take the inverse Laplace transform to find h of t, right? You can do all these, all types of such questions. I can ask, this is the differential equation, and the input is this. Okay, that's a good question. The input is this. This is the differential equation of the LTI system. What is the output? Will you be able to find it? Of course. From the differential equation, you can have h of s. From this x of t, you can have x of s. H of s times x of s will be equal to y of s. So you find y of s. And you find it like this, maybe. And then take the inverse Laplace transform of this expression to obtain the time domain signal of y of t, which could be the question that you need to solve. Okay? That's how things work.
Hocam bir şey sorabilir miyim?
Yeah.
H of S'in region of convergence ne oluyor?
We found it, actually. No, we didn't say it. The region of convergence of h of s includes the region of convergence of y of s, because y of s is in the numerator. Therefore, the region of convergence of y of s is determined by s plus 1 and s plus 2, which tells us that the region of convergence is greater than -1. For this question, if you're asking, you just have to look at h of s. Look closely what it is. And where are the poles? The poles are at -1 and -2. It is right-hand-sided. So the input is right-hand-sided, the output is right-hand-sided. Therefore, the system is causal and linear and time invariant. Therefore, we have to look at the poles. The poles are at -1 and -2. And the region of convergence is to the right of -1, which is the rightmost pole. But how can we notate or give an absolute expression about the region of convergence of h of s? I would say the region of convergence of h would be would include like this, the region of convergence of X, or something like that. Okay, that's the region of convergence expression, all that I can say. Sorry, not X, excuse me, Y, the region of convergence of the output. It may be larger than that. There may be some pole zero cancellations. I wouldn't really look at this kind of an expression. I would focus to the expression of h of s itself. Look at that, and where are the poles of it? And according to those poles, please do decide on the region of convergence of h of s. That would be my suggestion. Okay. Now, I will quickly do another example, and this example will be a jump into the concept of drawing system diagrams, system blocks, which was also an issue in the previous examination, if you may remember. And we were using integrators for continuous times, but I didn't ask a continuous time question because I was waiting for this thing to happen. This is one numerical example. H of s is equal to 1 over s plus 3. This is the system response that we have. Therefore, y of s over x of s is equal to 1 over s plus 3. Now, can you draw the block diagram of it? The question may start from a differential equation, and then from there, you may come up with this observation. And at this point, now it's possible for you to draw the system diagrams, the block diagrams. If you do the cross multiplications, I can see that s y of s plus 3y of s is equal to x of s, and the differential equation is therefore d by dt y of t plus 3y of t is equal to x of t. So the question essentially starts from this point. With this differential equation, they describe the block diagram. How can we make an implementation of this using integrated blocks? But if you take the Laplace transform of it and get this, it will be easier. And we will continue from here and say that, let me write that equation again, s times y of s plus 3y of s is equal to x of s. And I want to isolate the y of s, which has the largest s coefficient, that is the highest order of s. For example, if in this expression there is an s square or 5s squared times y of s, that would be the y of s that I want to isolate. But for this one, there is only one, and that is s times y of s plus 3y of s is equal to x of s. So I'm not really isolating this one. Okay, be careful about that. On the left-hand side, I leave it like this. And at the right-hand side, I write it like x of s minus 3, it's an ugly 3, sorry, 3y of s, all right? Now, the isolated highest s power term will be isolated with y of s by doing this. Y of s is therefore equal to 1 over s times x of s, okay, minus 3 over s times y of s, all right? Or you may combine it into a single 1 over s if you wish. You can also write it like this. Both of them are okay. Now the thing is, this 1 over s here, okay, this one is an integrator. And previously we didn't have a notation for the integrator, and we were trying to draw it like a stupid integral symbol, okay, a clef symbol for the integral inside the box. Now we're not going to do it that way. We're not just going to put 1 over s inside the box. It means an integrator. Every 1 over s block will be the integrator, and the output or the input-output relation will essentially be like this. At the output, we have the output y. It doesn't really matter if I write it like y of t or y of s or whatever. Let me just say y, because that is the output. And that output is multiplied by -3. Okay. And at the input, I have an x. It could be x of t or x of s. It's the input signal I'm talking. Because when I write, actually the correct way of doing it is the output is y of t, the input is x of t, of course. They are time signals. But when I write it like this, sometimes the students get confused because I'm going to use a notation of 1 over s inside the blocks. And we don't really use t and s together normally. So you may be confused. So let me leave it like this. The input is x, the output is y. And -3 times y of s plus x of s is obtained at this branch, and then their summation is going into an integrator, 1 over s. Okay, it goes on like this, and y plus x all together times 1 over s is the thing that we get, which is equal to the output, that is y. So this is the block diagram that we need to draw for the implementation of this first order system. 1 over s plus 3 is certainly, h of s is equal to 1 over s plus 3 is certainly a first order system. And this is the block diagram. In our previous views, we were trying to convert this differential equation into an integral equation. We integrate both sides of the equation multiple times, as long as the most differentiated part becomes still an isolated y of t. So we, for example, for this example, we had to integrate both sides of this equation once, and then it would make y of t plus 3 times integral of y of t is equal to integral of x of t. Then the same block diagram would appear, but instead of this 1 over s, we were using this stupid integral symbol. But now it's easier to see, right? So that's why now I am able to ask such block diagram questions. If I give you a differential equation, will you be able to draw the block diagram corresponding to that? But this is a bad news, because you will be now responsible. But the good news is that I'm not very much interested in trying to minimize the block diagram by sharing the 1 over s components together, which was a puzzling thing, which was the puzzle for the first examination. I usually don't ask such things, but I may give you just the opposite of the question too, which is this. I give you this block diagram, okay, and I ask you what is the differential equation which relates the output y to the input x. What is the differential equation? Or I may ask you, what is h of s? If this is the block diagram from x to y, then in between, what is h of s? Or another question, what is h of t, which is the inverse Laplace transform of h of s? So if you're able to find h of s like this, from there on, things should be easy for you. You can find the inverse Laplace transform of this, which is e to the minus 3t u of t, right? And what's the differential equation? How do you find it? You say that this is h of s if you find it correctly. that h of s is equal to y over x, y of s over x of s. So make the cross multiplications, write it like this, and then take the inverse Laplace transform, convert it into time domain, which will give you this differential equation. So the question you have to ask yourselves, did you understand how to do this? If you don't understand it, that's a problem, because it's the easy part to understand. Doing it will require some further exercise by solving a lot of questions, of course. I will continue with a few more examples regarding these block diagrams. We will be seeing another first order example, and we will also be seeing or observing some examples of second order systems, because second order systems are still easy. You can still split the second order system into first order systems. But after that, things start becoming complicated, and drawing the block diagrams for higher order systems will become more and more difficult. But the opposite is not correct. No matter how complicated this may be, you should be able to find a way to find the system transfer function, h of s, for any kind of a block diagram that I may give you. You have to trace the equations. Y of s is multiplied by -3, and onto it x of s is added, and then that summation is multiplied by 1 over s to give you y of s. So you should be able to write this is equal to y of s for more complicated block diagrams too. Okay, now let's give a break of 15 minutes, and let's meet again at, let's say 15:10. 10 past 3, let us meet. Okay, until then, we can stop.